Let's take a look at section 2 for this unit. We're going to look at reflections. All right, so the first question we need to ask is what reflects light? And the answer to that is almost everything reflects light. Almost everything reflects light. There's a few things that humans have made that do not reflect light very much. Anything that's black reflects less light, right? The darker something is, the less light it reflects. The darker something is, the less it reflects. Because that's less light getting to your eye. There's a product called Vantablack, which reflects like 99.99% of all light, which absorbs 99.99% of all light. It's made out of tiny carbon nanotubes. So these are tiny tubes of carbon atoms. Carbon atoms are very good at absorbing light. You've seen coal or just chunks of charcoal, which are black. And so they make it into tiny little tubes. And it absorbs so much light that it's really unreal when you don't see it, I guess. When you get a color, like this here is the color blue, right? This is the color blue. So in white light, there's all the different wavelengths of color. And the white light hits us, all these different wavelengths of color, red, orange, yellow, green, blue, indigo, violet. And this absorbs all the colors except for what it reflects, or thereabouts. It's not really precise. It will reflect like multiple colors. An object of a specific color will reflect that color of light and absorb the others. Now this gets a really big asterisk by it because it's not wholly true. Because you can fool your eyes into thinking something is yellow by shining something red and blue, by giving it red and blue light. And they'll think it's yellow. Okay, so it's how a computer screen works. A computer screen is made up of hundreds of thousands of little red, green, and blue dots. And those red, green, and blue dots emit red, green, and blue light at different intensities, fooling our eyes into seeing colors. But really, all the color that comes from the monitor is red, green, and blue light. Okay, so we can fool our eyes into seeing colors. Now, when we're talking about reflecting, there's a few things that we need to talk about. So we're going to draw a quick diagram here. So here's our surface. That's what's doing the reflecting. We have a blue light wave coming in, and we just draw it as a straight line. So this is called our incident ray. And our incident ray, it's this light wave coming down and hitting this surface right at this point. Then we've got this other line right here. And I'm just going to extend it up a little bit. This is called the normal. The normal line is perpendicular to our surface. Now, if it's a flat surface, it's easy to draw the normal line. But on a curved surface, it's perpendicular to the surface right at the point where it joins, right at the point where it touches. Then, a reflected ray, and I'm not being very precise here. I should have myself a protractor. I got a protractor here and all this. Okay, so I can, let's see how good I did that perpendicular line. Not bad. So this guy's coming in at this angle right here. It's going to reflect out at the same angle. So that's to right there. This is our reflected ray. And the fundamental rule is the angle, we use the symbol theta for angle, our angle of incidence equals our angle of reflection. Okay, so our angle of incidence equals our angle of reflection. Now, we are mostly going to be just dealing with light when we're dealing with reflections, but this same principle occurs with other things like water waves or sound waves. So, for instance, and you don't need to draw this, if these are water waves coming in like this, when they reflect, they will reflect out like this. Right, this is the wave front. The wave's traveling this way, and then the wave would reflect out this way. Now, it'd look a lot more complicated than that because parts of the wave hit here and reflect out, but the same principle applies. Right, diffuse versus specular. And two words that you should know. Diffuse is like matte finish. Specular is like glossy. A diffuse surface, in a diffuse surface, the reflected rays don't come out parallel. So in a diffuse surface, diffuse, parallel incident rays are not reflected parallel. This is usually because of a rough surface. Now I'm going to put a little diagram here. So I've got like a little bumpy, slightly rough surface here. Okay, and then I've got three parallel rays coming in. One hits there, one hits there, one hits there. Now because this surface is a little bit rough, we've got ourselves a rough surface. This first ray actually reflects kind of like this. The second ray, it's a different spot and reflects out this way. And the third ray kind of reflects here. So you can see they came in parallel, but they left not parallel. Now you can think of this, right? This is like a matte finish on a car, right? There's no shininess to it, right? This is not shiny. Now, things kind of come in degrees of diffuse or degrees of specular. Perfectly specular would be like a mirror. Paper is pretty much perfectly diffuse. Paper is white. It reflects all of the colors of wavelengths. But I cannot see a reflection in it at all. because it's very diffuse. The light that hits it is scattered in all different directions, right? I can't see a reflection of a pen in there. I can see the shadow of the pen, but there's no reflection of the pen. So specular, we'll just do a little diagram for specular. Parallel incident rays are reflected parallel. Right, this is usually a very shiny surface. Right, we've got some parallel incident rays. 1, 2, 3. And they get reflected off in parallel. 1, 2, 3. You can see a nice image in this. This is like glossy. Right, so on these, in a diffuse surface, some of the light rays even get reflected back. This is why road surfaces are better if they're a little bit rough, because the light from your headlights comes and hits the road, and you don't want the light to all shine forward, otherwise you don't see the road at all. You want some of the light to hit the road, and you want some of that light to be reflected back to you. If you drive on really black asphalt and there's a little bit of rain giving it a very smooth surface, you can drive and you can't see the road at all. Your lights, the lights from your headlight will just hit that little perfectly glossy surface, the little bit of water on top of the black, and they'll reflect forward. And the road will just be pitch black. It'll be like you don't see anything at all. I mean, you might see the little reflectors that they have in the road, but that's about it. So having a diffuse surface is good for something like a road, wherein you want the light to reflect all over the place so you can see the road under your headlights. Paper, it's very good to have paper diffuse, right? So you don't have shiny things in it. You're not looking at reflections when you're trying to read a piece of paper. It's good to have it be diffuse. Now, these are not absolutes, right? It's not like something's diffuse and something's specular. A mirror is perfectly specular. Paper is diffuse. If you look at a whiteboard is kind of specular, kind of diffuse, right? It exists on a spectrum, right? So some things are kind of diffuse. You can kind of see a reflection in them, kind of specular. You can kind of see a reflection in them. Some things are kind of diffuse. You kind of can't see. It depends on the material. And so it's not one or the other. It's a spectrum between the two. Right, so reflections in plane mirrors. Plane mirrors just means flat surface mirrors. Okay, so here we've got three objects. We've got an eye. We've got an object. We've got a mirror here. The light, some light is going to go off this object, bounce off this mirror, and into the guy's eye. Right here, his little pupil right there. So it's going to bounce off right into there. So some light is going to travel from here, going to hit the mirror, and bounce in. And where it hits has to be exactly halfway between these two. Now, how do you find out halfway between these two? Well, here's a small secret. I've got this object. I measured my distance from the mirror. This object is approximately 2 centimeters from the mirror. So I'm going to draw another object exactly 2 centimeters on the other side of the mirror. Same object. So it's got the same start. See, I'm just perfectly level. And the same top. I use my dots as a guide. I've got dots on this paper. I don't know if you can see them. So right here is my image. There's my image. Now we can trace the rays as they would go from the image to the eye. So I'm going to connect so here's a light ray hitting the eye, and that light ray would come from the top of my object. And now because I did that, this point is exactly halfway between these two, exactly half the height. Now I can also do that from the bottom of my image like this. There's my second one. There we go. So my light ray will travel from my object, hit the mirror, and bounce to the eye. This point is exactly halfway between these two heights. Now my image. We can talk about my image. My image is over here on this side. In a plane mirror, your image is upright. Right? It's not flipped over in a plane mirror. It is imaginary. It's not real. It doesn't exist. It just looks like it exists. It's the same size as the original. And it is behind the mirror, the same distance. Right, so this is upright. It's imaginary. It's imaginary because these two lines are going apart. It's the same size as the object. The image is the same size as the object. And the image is behind the mirror, equal distance from the mirror as the object was, right? This was 2 centimeters, so this was 2 centimeters. Okay, now, if we look at these, the angle of incidence will equal the angle of reflection here perfectly, if we drew this nicely. Let's look at the bottom. Ugh, what happens when this... Well, we do the same thing. Well, the bottom of this is about 1.9 away. So we put the bottom of my object here. That'll be 3.8 right there. That's the bottom of my object. Now we go up and we look at the tip, and the tip is now what? 2.3, so it'll be 4.6. It'll be right here. Right there is where my image will be. Now we can do the same process, okay? So we go from my image, right? Which if I just look up, if I position this straight up and down, you can see this is straight across from the mirror as this is straight across from the mirror as this. So now my rays from the top to the eye, like this. Now, if we were to line this up so that this is horizontal like that, and we were to draw the normal from the mirror, we were to draw the normal line right here, the normal, we would see that our angle of incidence equals our angle of reflection right there. Right, our normal is perpendicular to the mirror. So then our bottom one, I'm just going to do in purple. Looks like this. and looks like that. That's how that guy would look. I did that by knowing that on a plane mirror, the image is perfectly symmetrical. Right? If I folded this over, my image should match up with my object. And these are the terms that we always use. We often use arrows for these. And we can see here that our image, again, it has to be upright. Right? If I put my mirror vertically, right, my image is kind of the same as the other one. Upright. It is imaginary. It is behind the mirror. Equal to distance from object. Distance. Sorry, just equal distances. Right, these two are both equal distance from the mirror. And it is the same size. Right, and you can see here that our angle of incidence equals our angle of reflection. It's just hard to figure that out sometimes when the mirror is at an angle. All right, so also if we turn our mirror so that it's perpendicular, we'll notice that this is halfway between these 2 points. All right, so that's some reflection information. So on reflection, remember angle of incidence equals angle of reflection, and angle of incidence is always measured from the normal. There's some readings right there and questions to do from the textbook.